All right, so this was a big week, and we tried to go from at a very high level silicon to diodes and transistors to digital logic to ALUs and CPUs to microcontroller architectures, their instruction sets, their memory layout, how a CPU works, to writing code to them and getting it onto them so that they actually work. So we covered a lot in class. In this video, I just want to quickly walk you through basically the assignment, and I'm going to just do the more or less do the assignment. But I'm going to do it, and I haven't done this before. I'm just sort of like tackling this without seeing it, so you'll see exactly my process for making decisions and how to do this. I want to point out that what I'm going to do here, which is make this ATTiny board, is only one part of what your assignment is this week. We have this burn the bootloader slide, which we're going to turn a nano into a UPDI programmer. And these are the different links. So they will be very important and useful for you. It's not too hard to set it up. It just requires soldering the header, but bending out one pin and connecting it with a resistor, and then adding this little capacitor here, which it doesn't have to be a surface mount capacitor. It just has to be 10 microfarad capacitor. So this should be hopefully relatively straightforward. And then we need to use the Arduino software to load in this JPEG to UDPI firmware onto our Nano. So this is the instructions. You can see there's a Arduino file type that you can literally find at this GitHub link, and you should be able to select your board and upload this Arduino file just like you would, and then it should work as a UPDI programmer. So that's just a little reminder. These are links to 3 people that have done exactly the same thing, turning this Nano into a UPDI programmer. I don't know that that one's particularly more insightful, but here's one with a video for you to look at. So that could be potentially useful for you. So just take a look as a reminder. And the other thing that I would really love for you to try to do is to move on beyond Arduino. And for that, I've just sort of pulled up my VS Code instance, and I went to extensions and I typed MPLab, and I installed this first one, which installed a whole bunch of different useful extensions alongside it that should let us easily write code for our ATTinys, which we will get into in a later video. So those are just a couple of things that I wanted to remind you of on our way to being able to actually program this ATTiny board directly using a programmer and a software stack that is supported by the manufacturer. So this is sort of sidestepping. We're getting into the real underlying thing that happens behind the scenes, not just this sort of Arduino abstraction, and we're unlocking the full power of the microcontrollers we're using. Okay, so our goal is to make the simplest possible board for the ATTiny, and I'm going to do the ATTiny412. I believe that is the one that you're going to use. It's probably the simplest one to use, and it only has 8 pins, so it's a really good one to start with. So I just created a new project and labeled it Forge ATTiny412 and open it, and this is a completely empty project. So there is nothing here. So perhaps the first thing we should do actually is open up and take a look at the data sheet, just to kind of like get ourselves acquainted with what's going on and potentially make some decisions. So you can see I just Google ATTiny412. We could go to the product page. I see this other link here is a PDF that's 500 pages, which is probably the data sheet. So I'm going to go ahead and just click on that one. But we could also just go here and it will be listed somewhere. There's going to be almost always documentation. So you can see we have a documentation tab, and then we have the automotive data sheet and then the normal data sheet. And we'll just look at the normal data sheet once again. So same deal. And we can see some really nice things about our microcontroller, right? And this is what you're going to be reading as part of your assignment. So we can see it uses AVR. That is the instruction set that this CPU uses. So unlike, x86 or ARM, this is actually its own, it has its own specific instructions that it can run. That's a smaller, more easy to understand set because it's a smaller, less powerful microcontroller. It runs at 20 megahertz. So you might remember, your computer probably runs at 3.3 gigahertz and has like 6 cores or something like that. This runs much slower and only has 1 core. It has interrupts, so things outside it can watch and wait for something to happen, and it'll interrupt what's going on and sort of tell your CPU what's happening. We can see how much memory it has, both the ROM that is non-volatile and RAM, which is volatile. We can see that it has a few different options for how fast we run it. So even though it can go up to 20 megahertz, that's not necessarily how fast we're going to run it. There's some trade-off with power and speed. We can see if they tell us that we can use UPDI to program it. So that's important. We want a chip that uses UPDI since we're making UPDI programmers. That's the newest way of programming these chips. That's great. We can put it in standby mode, and we can see what kind of peripherals it supports. So we see, it has some timers. It has this USART or UART. UART is a subset of USART. That's a very common serial interface, SPI, I2C, some an ADC that's 10 bits, all sorts of great stuff. And then it has a few different packages, and we're using the 8-pin package, but you can see we can actually, if we need more pins, if we want to sort of turn on and off more LEDs or do more advanced stuff, there's even more pins. So great. And we can start to read all sorts of wonderful things about our device. So that's really useful. This will give us an overview of like why we would pick this chip, how it actually works. The nice thing is, and what is generally true with a lot of these, so you'll see in this sort of like basic little outline, they have an external clock, but most chips are able to generate their own internal clock. And we saw that that was true for this one when we were reading through these clock options, right? We have an internal oscillator and an internal oscillator. And so it has something inside of it that can generate a clock for us rather than using external crystal. So we don't actually have to do anything for the thing to turn on and for it to start running with a clock. So that's great. We do need to give it power. So we should look and see what kind of power it's capable of accepting. And we can see this is our little 8-pin package that we're going to use. We have a pin that's going to be our power, our ground. We have our UPDI programming pin. And then we have a few other ones that we can probably reconfigure around here for our different purposes. If we want to use an external clock, we're going to have to use this pin for it. Otherwise, we can reassign it. So that's useful to know. And we can see everything each pin is capable of doing, right? So this is, now we're starting to get into useful territory, right? So we can see if we want to do an I2C interface, we know we need an SDA and an SCL line, and that's only going to be able to be assigned to PB1 and PB0 or PA2 or PA1. And there's some little extra note for us to look at, 3 alternate pin positions. For selecting these positions, we have to do something extra. We have to talk to this multiplexer thing in order to set this up. By default, it's going to want these two. So that's really useful information for us if we're going to try to add a breakout for our I2C. And that's probably the only thing we're really, looking for that we really care about. Obviously, we need this special UPDI reset pin broken out for our programming, but it's already called that out for us as PA0 when we look back at our little pin designation for the package we're going to use, which is the 8-pin package once again. And so you can see PA0 is UPDI as they've described. If we go back down here, we have SDA, SCL as PB1, PB0. Let's look at our package. Oh, we don't have PB1 and PB0 broken out for us. That's only if we use one of these bigger packages do we get that one. So that's sad. So we may have to use PA1 and PA2, and then we're going to have to like set some configuration bits probably in order to do that. So PA1, PA2, let's see if we have those. We do, PA1 and PA2. So we know these are going to be the two pins that we need to break out for I2C if we're going to do them. And then let's just check what voltage level this accepts. So I'm going to search for VDD because I know that's what I'm looking for. And we're going to get past this little bit. Let's just see. So we're going to get lots of different information. It may not be the most efficient thing. It's going to pop up a lot of different places. So maybe actually what we want to do is search for this absolute maximum ratings table, which is a very common table that you will find to just give you a sense of what's going on for your board. And we can see our power supply voltage is right here. It's the very first thing. And this little chip can run as long as it's less than 6 volts. It's not going to be sad. So that's good. And then we can run down and we see general operating ranges, and our operating supply voltage can be anywhere between 1.8 and 5.5 volts. So we can run this chip off of 1.8 volts, which is common, 3.3 volts, which is common, and 5 volts, which is common. Those are kind of the typical voltages we would potentially run this off of. So that's great. And what it's going to be able to do in terms of speed, as we can see down here, is different depending on the voltage level that we're running it at. So you can see, there's certain speeds that it cannot do 10 megahertz with 1.8 volts. It needs to be a minimum of 2.7 volts. It can't do 20 megahertz with less than 4.5 volts. So this is just useful information for us to know. And this data sheet is going to be full of really interesting information, but what I'm doing now, just pulling out these very specific things, is how you will start to use a data sheet once you've done enough work with microcontrollers to really understand what information is relevant for you. Okay, so anyway, that's great. There's a lot of useful information for us that we've already pulled out of there. And that's the way we could do it if we're using the data sheet. The other place I would immediately actually look if I'm going to be making this board is I'm going to look up Neil Gershenfeld's How to Make Almost Anything, ATTiny412. Let's just see if I can find it immediately. And we're going to be greeted with people doing these projects. And they may even, they'll show us some code that they wrote, right? So that's great. So these are always going to be useful for us to look at. And you can see this wonderful person has broken out the 412 for us. They even have a nano here for some reason. I don't know if they're using it to program, but anyway, we can see that there's some evidence of that. But let's just actually look at the How to Make Almost Anything website. And we'll just go to electrical design. Scroll down. Is that where we want to be? Nope. We'll go to electronic, maybe embedded programming, actually. Yeah, here we go. And we'll scroll down to our ATTiny412, and we'll just actually look at one of these boards. So, and I'm going to look at the traces. No, I'm not going to look at the traces. I'm going to look at the components. No, I'm going to look at the board. Yeah, so there we go. This is nicely broken out labels for us, which is wonderful. And we can see a working board that Neil has made, right? And so this has the UPDI programming pins, an LED with a resistor to ground that we can control, a power bypass capacitor, as we've talked about, which is a really nice thing that you should have. And we will power this board. We will program this board using this header. And we can also power this board using this header by plugging in VCC and ground. And we can actually power it off of 1.8 volts, 3.3 volts, or 5 volts here. So that's great. So that's wonderful. Here's a working design that we could also reference, and we can look at which pins are connected where, and we can be very confident about what we're doing. Okay, so we're ready to go. So first thing I'm going to do is type the A button, let it load up. And I'm just going to search for ATTiny412, and hopefully it is here. And look at that, we have it, and there's an 8-pin version of it. So we are in great shape. We can just click on it and drop it in, and we're already almost there. Okay, let's go ahead and add a ground. Amazing. We'll drop that here. Let's go ahead and add, let's just say, let's add power. What do we have? Power flag plus, we probably want like a plus, we could do plus 5 volts power. That's a nice thing to do, a nice way to do this potentially, which is just like the ground. And now it's going to function exactly like our ground. Now we can just put these anywhere and we know it's going to work for us. Okay, great. So the next thing we need is, and probably the most important to kick us off, is our 3-pin UPDI programmer, which also will give us power. So let's go ahead and add. And we know from last time that CONN is how we get connectors, right? And we're going to need a 3-pin one. So I'm just going to type in O1X03. Then I know that that's going to give me this kind of generic connector. We're going to have to find the right footprint for it. But that's going to be our UPDI programming header. Wonderful. And I'm going to go look, I'm going to reference back to Neil's, and we see his is VCC, ground, and UPDI. So that's the order that he has done it. 1, 2, 3, VCC, ground, UPDI. Let's take a look. Let's just cross-check. We're going to be trying to plug this into our nano. So let's just make sure that we also match the nano pinout of the programmer. So if we go back here and we open our programmer, I just want to double check that the pinouts match, because it would be really nice for us to be able to just plug it right in and not have to like rewire it up, because we're getting these pins out here, which are going to be our programming pins, right? So let's see if we can kind of assume what is going on here. And this is making me feel a little bit less excited because this looks like it might be different with maybe positive voltage ground and the UPDI programming pin in the middle. So I'm not totally sure. That's different, a different pinout than the pinout that we saw from Neil's VCC ground UPDI. So let's just read. Let's just take another deeper look and try to see what we expect if we do this. Let's see, they had it plugged in over here. Do we see anything that tells us the pinout? No. Okay, and so we probably want to take a look at, we could look at the other links. Maybe they tell us exactly what the pinout is and we don't have to think too much about it. We could also look here really fast and see what it seems like is happening. So it looks like that resistor is likely the UPDI pin, and it seems to have broken out vtarget UPDI ground, and this coming off of pin 6 for the programmer in the software. So I'm just going to guess that when we're looking at this and we see pin 6 with the resistor in the middle, that's the UPDI programming pin. And then we're going to expect the high voltage and ground to be on either side of this. And we could actually check, because these are plugged into our ICSP, our in-circuit serial programming header that's common for almost all Arduinos. We could actually look that up, right? So we could actually look ICSP header pinout, and it will, if we look it up, we'll actually see the pinout, and this is ground pin, and this is our voltage pin, right? Maybe a little bit unclear VCC and ground, right? It matches on these two images. So we could actually go off of that and figure, because the way that this is wired, we know a couple of these pins are plugged in and they're pulling ground and VCC off of these pads. So you can see soldered for ground. So then this one is ground, which also again matches this. So they have ground programming, and plus, which is actually different than the order that Neil has here. Why would we do that? Why would this order be different? Well, the order is likely different because of the ease of routing these traces. You know, he's pulled VCC here, ground here, and getting UPDI in the middle here, which would probably be the easiest if we wanted to just butt up our two connectors, actually requires crossing the ground unless we pull this ground around, and then we could have VCC, UPDI, and ground. And I would prefer to match the pinout of our programmer so we can just perfectly connect them together. But it's not that big of a deal if we have to reorient and use a cable and turn them around. It's not the end of the world. But ideally, we want to kind of like match this so that it's idiot proof, right? So so I'm actually going to go ahead and sort of mimic this and put my pins as ground, UPDI, and VCC, and or on this board, what we're going to get is like VCC, UPDI, and ground. It doesn't really matter, you know, I can turn the cable. That doesn't really matter as much. What matters is UPDI is in the middle, in my mind. Okay, that was a lot to talk about, but this is a very important thing, is sort of matching, you know, pinouts and thinking about how they're going to orient and making it easy for you not to accidentally connect it in reverse or do the wrong thing, you know? So it won't be catastrophic if you reverse, if this isn't plugged in and the only way it's getting power is from your nano, if you reverse VCC and ground, it's not going to be catastrophic. It's just not going to work. So, you know, that's something we don't have to worry too much about, but we do want to double and triple check that our outputs from our programmer match the inputs that we're expecting, and it's very easy to make a mistake of orientation. Okay, so that was long-winded. Let's go back to KiCad, and let's go ahead and just sort of say we will, I'm going to rotate it this way, and sort of in looking at the footprint that we're expecting, I'm just going to go ahead and put VCC on this side. So that will be my 5 volts. Copy paste. I'm going to copy paste my ground, RR to rotate. And then this needs to go to which one? PA. What is this? Also, he's rewritten this number, and unfortunately, this little schematic, this little representation here doesn't tell us which pin that is. So let's just cross-reference and make sure we're definitely getting the right UPDI pin from our data sheet. So let's go take a look back at our 8-pin pinout, and we can see it's in the same location, and it's PA0, pin number 6. So let's just make sure we have PA0, pin number 6. Great. So we've done that part successfully. Amazing. All right, what else do we need? Okay, so we've hooked up our UPDI programmer. This is also going to give us our power. Wonderful. One thing that we are missing, if we take a look at Neil's example, is a bypass capacitor. And it's always good to just drop in bypass capacitors everywhere you possibly can. And so I'm going to do it this way, which is I will add in a capacitor. Amazing. I just typed C, and it's the first thing that pops up, and drop it over here. And guess what? I'm gonna just do this. We just want this capacitor, as we know, it's just sitting close to our microcontroller, and it's just holding our power line. It's letting any noise, any little vibrations on our power line, shunt them to ground. Otherwise, it keeps our 5 volts sitting at 5 volts. So this just cleans up our power supply close to our chip. And you will frequently see in schematics a little section, which is just a bunch of capacitors that connect power to ground sitting up somewhere. And this is how we do it. So we know that this is going to sit here, actually, like right next to our chip, just like we see in Neil's example, right? It's right next to our power and ground pins. But we can also just kind of like make our little bank of bypass capacitors and kind of put them off to the side in our schematic and not even really think about them too much, and just know that we should do that when we're doing a design. So I will frequently in my designs have a little section up here, which is just like bypass capacitors. And frequently it's good practice to actually have like 1 microfarad and 100 nanofarads, or like one really big one and one medium-sized one, in order to even do a better job of cleaning up our power supply. That's very common. But we're just going to do one, and we'll mimic Neil's, this is going to be a 1 microfarad capacitor. So we'll just click on it and call it 1 microfarad. Wonderful. Okay, and now we will do an LED. 1K seems like quite a large resistor for the LED. I'm kind of surprised. It should be fine. So if we go back to our LED, let's just say, once again, we're going to pick our 1206 SMD. Let's say we do like a blue LED data sheet. Most LEDs are going to be very similar. So we just find some random data sheets. And okay, so this one doesn't have our graphs. Let's just pick one that has the graph. Oh, this one also doesn't have this tells you how much data you typically need about an LED. You really don't need to check it usually with that much detail, but we're going to, for the sake of this, if we can find a real data sheet. Let's try. Okay, so this is a real one. You can see we get the relative luminosity by angle, which is really cool. There's all sorts of wonderful things we can do with these kinds of data sheets. But the point that I just wanted to make is, we have this relative luminosity table where, I sort of said in class, we typically pick 20 milliamps, and this data sheet tells us that's normal. That's 1 on our relative scale, right? So it sort of is indicating to us that 20 milliamps is what we're expecting. But if we add more resistance in our current limiting resistor, we would expect our current to go a little bit down. And all that's going to mean is that we're drawing less current from our microcontroller, and we're going to get less luminosity from our LEDs. And those LEDs are super bright. So picking a value, even though Neil, in this little example here, has picked a value that's an easy, 3x what we would normally think of as a typical current limiting resistor size. And that's just based off of the math, of like 5 volts or 3.3 volts and what voltage drop we're going to get on that LED, given that 20 milliamps of current, and that, we get our size from that. This just means we're going to have a slightly less bright LED in this circuit. So I think that's fine. It's actually kind of like conservative to pick a 1K resistor. And I'm not going to do the math. I'm just going to go ahead and pick this, and we're going to go for it. So let's do our PA3, and let's just do exactly the same thing. So we're going to add, we're going to type R this time. We put a resistor in. We're going for PA3. Amazing. I will, add my little wire here to connect. Now we're going to add our LED. Just type in LED. There's an LED. We'll rotate. Amazing. And then, of course, this needs to get connected to ground. Lovely. Okay, so that's great. And then the last thing that I've sort of alluded to is we would love to do an I2C header. And there's another thing that we've talked about, which is I2C requires pull-up resistors, and our microcontrollers are just able to pull down the voltage to signal to each other, right? So one thing we could look up in our data sheet, or try to figure out from our data sheet, is, does this have internal pull-ups? So we could actually just search for pull up with a dash. Let's see. General purpose input and output pins with individual configurations, pull up. So that suggests maybe they do have internal pull-up resistors inside the chip. So we don't even have to put one on there. So let's just read a little bit more. The IO pins, there are 8 IO pins, port A, port B, port C. We can multiplex them, etc. There's a data direction. There's some other stuff. They're synchronized based off of a peripheral clock. So they don't use the same clock. There's a slightly different clock that they use when we're timing our peripherals. All pins are individually configurable. Okay, that's great. And we see a pull-up enable on our block. And we can, so that's really great. It seems like all of our pins are going to have a pull-up ability. So we probably don't need to add any pull-ups, which is wonderful. And let's see, does it tell us how we would set that? Each pin, let me just keep searching for pull-up. So I have my pull-up down here. The pin in control is used to convert inverted IO pull-ups and input settings. Okay, cool. So look, we know exactly what register we need to set in order to set our pull-up value. If we look down at the register map, which we get at the end of these sections, we can see there's a control register for each particular output, and there is a single bit that, if set, will tell us that we're using the pull-up or not. And if we click on it, it'll take us to a section showing us this control register, and we can see this sort of fourth bit. If we set is read-write bit, so we can read it and see what this is set to, we can write it. And if we look at it down here, if it is 0, the pull-up is disabled, and if it is 1, the pull-up is enabled. Amazing. So we can actually tell our thing by setting pin, whichever pin we're using. We can set this bit to set the pull-up and have a pull-up available to us. So we don't need to add pull-up resistors outside of the chip. We can just break out our SDA and SCL chip as long as we remember to set this to 1, because by default, when on reset, it is going to be 0 and the pull-up will not be enabled. So this is wonderful. Good news for us. Okay, so what does that mean? All we have to do in order to break out our I2C for later use is add, once again, another connector. We can do a connector that is just the SDA and SCL pin, but that's going to be a little bit of a pain in the butt for us, because in order to connect this to some other device, we're going to make sure that they share voltage and ground as well, right? So if we plug in a little power supply to our UPDI pin here and turn on our microcontroller, that any sort of peripheral I2C device also gets power from our power supply and needs to have a shared ground if it's going to be communicating with us. So instead of breaking out just those 2 pins, I'm actually going to look for a connector that has 4. Awesome. So I'm going to put this 4 connector pin over here somewhere. And then we're going to go back to our data sheet really fast and just look again at where our I2C pins are. So I type I2C, that's probably not the fastest way. We probably want to look at our pinout. Okay, I remember saying it was like these two, PA1 and PA2, but let's just double check IO considerations. Okay, let's look again. SDA needs to be PA1 for us, okay? And SCL needs to be PA2. Okay, PA1 needs to be SDA. So one thing that we can do is add labels to some of these pins. So I haven't done this with KiCad. Like I said, I actually use Altium mostly, and I'm not like I'm just really a novice, just like you, when it comes to using KiCad. But we're going to make a new label, and we'll make it SDA. And we're going to make another label, and we'll make it SCL. And we're just going to try to do this because it's a useful thing to do. So we have SDA now, and you can see it gives me a little dot. And I'm going to go ahead and, as we said, PA1 from my data sheet. PA1 should be SDA. And then this should be SCL, which apparently I need to add a new one. Let's try that. SCL. Okay. So will it give it to me? No. Maybe I need to do this. No. Well, we're learning on the fly here how to do this. Let's see. Show name, line center. Yeah, I'm kind of surprised. SCL. Well, I thought oh, it's giving me this. Interesting. SCL. All right, let's just give it a try. Let's see how well we can work with these. So I'm gonna set it up so it should be now connected to PA2. Let's just double check again, PA2. You know, and this again is also very common, and it keeps your schematic very neat, right? So instead of drawing lines that are intersecting this, or you know, I could bump this line up so that these lines can get over to this connector. Instead, I'm just going to add in these labels, you know, and that just makes it nice and easy. And so let's just go ahead and copy paste everything over like this. And now here we go. We got our SDA label, and you can see it's not connected because it sort of labels on this corner over here. So we're going to add our wires. We're going to connect that to that and that to that. And now we have an I2C pin as well. Okay, great. So we have successfully created a wonderful example circuit here. Let's do one more. Let's just do one more thing for posterity here. So I'm going to bump these over. Here's the stretch, another stretch goal. Let's add a button. Let's see if I search for button switch. Yeah, we should, I guess I should probably call it a switch. SW. We just want a single pole, single throw, or a push button switch. Perfect. So let's just grab a push switch like this. And as we have seen, I'm going to rotate it so that it's face up, face down. PA9 or PA7. Maybe I'll go to PA7, PA6. I know these are general purpose IOs. We've used the ones that we care about that have a particular use. And we now need to do what we have sort of learned to do with the buttons from class, right? Which is we need either a pull-up or a pull-down resistor in order to make this work. So I'm actually going to kind of move this a little bit closer so I have a little bit of space. I'm going to grab my 5 volts. Put it over here. Move this down a little bit. I'm going to grab another resistor, rotate it. I'm going to put it there. And we didn't label this one, but we know that's going to be 1 kilo ohms. So I'll just write 1 kilo ohm. You could just write 1K. You know, that's also very common, 1K. And this one, I'm gonna make it a generic sort of pull-up size, which would be something like 4.7K potentially. And here we go. We're getting very close to a working button, right? So we've looked at this in class. Hopefully this makes sense to you, but just so we're all on the same page, when this button isn't pressed, we have 5 volts passing through this resistor into this, and this has a high input impedance. So it's like a super big resistor. So almost no current is flowing, and it's almost like there's no voltage drop on this very, relatively speaking, tiny resistor. And so this is sitting basically at 5 volts, which is wonderful. It's pulled up, we call that a pull up. It's pulled up to 5 volts when nothing is connected. And then when we press this button, it's pulled down to ground. So we can sense when this button is pressed because this will change from a high signal, a 5 volt signal, to a ground signal. And of course, when we press that ground, this 5 volts gets connected to ground through this resistor and some current flows through it. And if we didn't have this pull-up resistor, it would short these things together and that would be very, very bad. So that's what this resistor is doing for us in this case. Okay, so we have successfully done an entire circuit layout where we have an LED we can turn on and off, a button that we can sense on an input, a I2C broken out connector, and a UPDI programming pin, and a bypass capacitor. You have successfully created a schematic for your design for this class. All right, I'm going to go ahead. This was long, so I'm going to go ahead and break this into 2 videos, and I'm going to continue onward and actually make the board and sort of double check our footprints so that what we have will actually work with our single layer board for this little part. Okay, so I'll see you in the next video if you would like to continue to play along.